Hello students, welcome back. We completed determinants of order 1, 2, and 3. Actually, we did determinants of order 2 first, and then order 1, and then order 3 in that order. Now let's go over to determinant of arbitrary order, but some preparation is in order, and here we go. Let's begin with the concept of deleted matrix. I already introduced you the term, but let's do it formally here. Let A be an n by n matrix. The deleted matrix capital Aij is an n-1 by n-1 matrix obtained by removing the ith row and the jth column of A. So we are looking at Ij. So Ij column, Ij entries here. So ith row, jth column, those are gone. Here's an example. If we have A like that, and what is A23? A23. Okay, we are deleting second row, so that's gone. And third column, delete. And that is the deleted matrix A23. Easy? Indeed. All we have to do is to cross out. Delete, delete, and that's what we have. Another example, A41. Fourth row, green, and first column, green. Delete those out, and what's left is the deleted matrix 41. How about A52? Actually, that's a little bit different. What's the difference between these? Uppercase, that's deleted matrix. Lowercase, that's just the entry. So, fifth row, second column, and that entry is -2. So this A51 is -2. When I write, I'm going to use capital for matrices and deleted matrices, and then small, lowercase for entries. But when I speak, most of the time they're going to be just A's, so you'll have to understand me appropriately. And that's part of mathematical maturity as well, so I offer no apology. So uppercase, lowercase, they mean a little bit different. And here's further subtlety here. What is this A5 here? Superscript 5 means it's a column vector. So fifth column vector. And then A6 subscript means row vector. Okay, sometimes the superscript may confuse you with power, the repeated multiplication. So I'll make sure that I'm talking about the column vector each time. Okay, all right. So much for the example. And finally, are you ready to begin the definition? The definition of the determinants of arbitrary order. Ready or not, here we come. Here is the definition. Okay. The determinant of A, an n by n matrix, is obtained by A11. I think I need some help. A11, A12, A13, A14, A15, those are the first row. Okay? And we have these A11, A12, A13, and so on, with alternating sign, plus, minus, plus, minus, plus, minus, and so on, times the deleted matrix, the determinant of the deleted matrix. Here we go. What do you mean by A11? A11 came from here. It's over here. So remove the row and column where this A11 came from. First row, first column out, and what's left is this deleted matrix and that determinant. So we started with n by n matrix. So deleted matrix is n-1 by n-1. Next, A12, this one, and then remove the row and column where this A12 came from. So remove first row, second column. What's left is a deleted matrix A12 and that determinant. Similarly, A13, A14, and so on and so forth. Just following the first row. And is this a well-defined expression of the determinant? The answer is yes, because this is a recursive definition. So determinant of order n is defined recursively using the determinants of order n-1. And those determinants of n-1 were defined in terms of the determinants of order n-2 and so on. So if you switch the order, then you can go back like this. Determinant of order 2, we already know how to do it. It's this one, AD minus BC. And then from that, we can define the determinant of order 3. And then from the determinant of order 3, we can define the determinant of order 4. And order 4 to order 5, order 5 to order 6, order 6 to order 7 continues, and we cover everything. So yes, this is a good definition. The determinant of arbitrary order is well defined. And this sigma notation, well, what choice do you have? It's 3000 level course, so whether you like it or not, you had better get used to it. So all these are coming from first row. So A1J, so capital A1J, those are all 1. So they're all coming from 1. And the column J is moving from 1 through n. First column, second column, third column, and so on. So we have the sigma notation. And negative 1 to the 1 plus jth power, they represent pluses and minuses. Now when j is 1, we have 1 plus 1 here in the power. So negative 1 to the even power, so that's always positive. So 1, 1, and 3 always give you positive. Negative 1 to the 2 power. And then as j goes to 2, 3, 4, 5, and so on, we have 1 plus 2, 1 plus 3, 1 plus 4, and so on. So this power alternates from even, odd, even, odd, even, odd. Consequently, negative 1 to this power is alternating from plus 1, minus 1, plus 1, minus 1, like that. So that's the definition of the determinant. And then, no, not those just yet. Signs. Let's see, let's go to an example problem. And here's a nice example problem. 4 by 4 determinant. Ready? Okay, all right. First row, 2, 1, negative 2, 3. So, okay. Well, here's the formula, all right. And then 2, 1, negative 2, 3. So we have 2, 1, negative 2, 3. Those are there. And then signs, plus, minus, plus, minus. Is everybody happy with the sign? It's coming from first row, so plus, minus, plus, minus. Plus, minus, plus, minus. Okay, this minus is different. This minus comes from this sign, so all right. Now the deleted matrix. So from here, first row and first column out, what's left is this deleted matrix. That's the first. How about the second deleted matrix? Well, it came from, you see, this matrix here, and then I want this one. Okay, so second column and first row out. What's left is this deleted matrix. Next deleted matrix, I want negative 2, right? Negative 2. So this column and then that row out. What's left is this deleted matrix. Same thing, we have this deleted matrix, and then all you have to do now is to calculate these 4 3 by 3 matrices, and then do your computation, and then you're going to get what you want. Well, In this notebook, I used further reduction. If you don't want to use reduction, if you want to go ahead with the direct computation for determinants of order 3, this method over here, you'll have to do this 4 times, but yes, it'll work out okay. That computation is left to the students. And then here, I'll just go with the first row here, 0, 4, 0. So we have 0, 4, 0. I don't have to worry about these zeros. And then about this 4, we've deleted matrix 3, 1, 1, 1. Okay. How about the next one? 3, 4, 0. So we have 3, 4, 0. And then for 3, we have this deleted matrix. For 4, we have 2, 1, negative 3, 1, this deleted matrix. For 0, actually I don't have to worry about this part, but I wrote those anyway. And then how about this one? Negative 2 times is something we are going to do later, excuse me. The determinant first. 3, 0, 0. 3, 0, 0. I don't have to worry too much about zeros. Up to 3, removing first row and first column, we get this deleted matrix, which comes over here. And then similarly, we have 3, 0, 4, and then we have appropriate deleted matrices. And then we can calculate each. That's what we get in the end. I hope my computation is correct. But I'm not completely sure, so do your own and please check. Okay, that's how we define the determinant of arbitrary order. But that's not the end of the story, because n by n matrices have n rows, not just first row. So what if I want to use different rows? Well, it turns out we can do the same thing, almost the same thing. Sometimes it may differ by sign with respect to each row. And not only that, each column. Well, you saw all those for 3 by 3 matrices before. Here's an example. Instead of taking the first row, highlighted in blue, and plus minus, plus minus, plus minus, all these deleted matrices, what if I decide to select the 4th row? And then we have all these deleted matrices, fine. But then again, what about the sign? Well, typical scheme, plus, minus, plus, and then minus. So we have to start from minus sign. Alright, we have minus, plus, minus, plus, minus, plus, those kind of things, and deleted matrices appropriately. And then is that going to give me the same value? The answer is yes, and that's something we will prove a little bit later, but we'll have to prove it. But if I do it right, if you do it right, then this happens to be the formula. And not only that, you can do that with respect to any column. Here I decided to use a 3rd column. Alright, this is plus, minus, and then plus, and that's why we begin with plus here. And of course alternating sign, plus, minus, plus, minus, plus, minus, with all those deleted matrices, and then adding them up, delete like these. And that's another way to get the determinant, the same value. Now we took this as a definition using the first row, and the other expressions, the other formulae, do they also give you the same value as this definition? A big question to answer, and once we prove it, then actually I take it back. Even before proving it, we can just use it, but at some point we'll have to sit down and prove it. Alright, before proving it, let's go ahead with an example problem. And here's a nice example problem because at first glance, it's going to be far more convenient to use the second row here, we have a bunch of zeros. So even if we didn't prove it yet, we can still use it as long as we will prove it at some point. Okay, so let's go ahead and do it. So let's use the second row. So plus minus, so we have to start from minus. So we assign minus plus minus plus, and then the numbers are 3040. All right? Okay, this 3 times this determinant. How do you do? Well, let me simply take first row, 1, negative 3, 2, 1, negative 3, negative 2, 3 with plus minus plus, and deleted matrices. We got that. And this one, that's 0. So no worries there. And then how about this determinant? Again, I'm using the first row, 2, 1, 3, 2, 1, 3 with deleted matrices. And then finally this one, that's going to be, whatever that's going to be, that's just 0. And then if you calculate all that, you're supposed to get negative 14. And also, here, when you calculate this kind of determinant, instead of using this reduction, if you go over to crisscross directly, this method, just fine. To tell the truth, I use it this way. I do it this way. So I reduce up to order 3 and then go over to that crisscross method. But our textbook author and most of the linear algebra textbook I saw reduce everything up to order 2 and then use crisscross for order 2. Anyway, you're going to get appropriate value. Now, you can make some algebraic mistakes here because just look at this, it's complicated. So some computational method is going to be helpful, and you can use computer algebra system like this. You can express matrix as double brace for big list, and then each row with brace. 2, 1, negative 2, 3, 3, 0, 4, 0, those are all rows with all those braces, and then 4. And then show me the matrix form, and that's this. Show me the determinant, that's that. And then show me the inverse of A. And it showed me inverse of A in Mathematica's form, with braces and first row, second row, third row, fourth row like this. It's hard to read, so I'm going to ask Mathematica to calculate, excuse me, not calculation, show me in matrix form. And that's the inverse matrix in matrix form. And these are all useful commands. Those are all useful commands. Let's see, we have a little bit more time. Let's see, how about using columns? Using these 2, 3, 2, negative 3, 2, 3, 2, negative 3, and those determinants. Yes, you can do it this way too. And then if you do all these 4 3x3 matrices and calculate those all 4 of those determinants and then put them together, you're supposed to get the same value, but it's tedious, so I'm going to leave you here.